All right, let's dive straight into this explainer. We're looking at a pretty ancient, unrelenting enemy today: fire. In our modern built environments, fire isn't just some random accident. It's actually a super complex physical and chemical process that we literally have to engineer our lives around. So today, we're going to break down exactly how it sparks to life, how it moves through a structure, and honestly, the most important part, how we can practically defeat it. To really grasp the massive global stakes we're dealing with, just look at this totally staggering number. The National Fire Protection Association estimated the total cost of fire in the U.S. alone for the year 2014 at $328.5 billion. Let that sink in. That's roughly 1.9% of the entire U.S. gross domestic product for that year. We're talking about an economic impact that rivals major global industries. And the craziest part? The hidden financial burden is what really gets you. When we think about the cost of a fire, we usually just picture the obvious, right? Buildings burning down, direct destruction. But check out this breakdown. The direct property loss was $13.2 billion. But the indirect costs, stuff like passive protection, building maintenance, planning, insurance, that topped out at an unbelievable $159.4 billion. The sheer cost of just anticipating and trying to prevent fire vastly outweighs the cost of the actual property it destroys. So here's our roadmap for unpacking all of this today. We'll cover 1. The true cost of fire. 2. Anatomy of a fire. 3. The classes of fire. 4. How fire spreads. And 5. Defeating the threat. All right, Section 1. Anatomy of a fire. The science of ignition. Here's the crucial thing you've got to understand. Fire is not just a random accident. It's a very specific, self-perpetuating chemical reaction, and it relies entirely on what we call the fire triangle. For combustion to happen, you need 3 things to perfectly align at the exact same time: oxygen, heat, and fuel. Once that fuel hits its ignition temperature, the heat from the flame itself actually keeps the whole reaction going. It literally feeds itself as long as this triangle stays intact. Let's zoom in on the heat, or ignition, side of that triangle. The hazards here, they range from super obvious to highly deceptive. I mean, sure, we expect naked flames from gas equipment or heat from welding, but danger loves to hide in plain sight. Think about frictional heat or a static charge building up on mechanical conveyor belts. Think about poorly installed electrical cables getting way too hot inside a wall. Or, and this one always blows my mind, the spontaneous ignition of something as totally harmless looking as a pile of oil-soaked rags. To finish off the triangle, fire basically needs to eat and breathe. It eats fuel, which honestly could be just about anything: flammable liquids, cardboard packaging, plastics, high-piled storage racks, or even fine waste dust and wood shavings. And it breathes oxygen. Usually it just pulls this right out of the normal atmospheric air flowing through open doors or being pumped in by AC units, but it can also draw oxygen from specialized oxidizing chemicals, like peroxides, which actually act like a supercharger and make the fire burn even more fiercely. Moving on to Section 2, the classes of fire, identifying the threat. So, fires are officially categorized by whatever fuel they're eating, using international ISO standards. First up, we have Class A fires. These involve your ordinary carbon-based solid materials: wood, paper, textiles, furniture, stuff that usually leaves behind glowing embers. Then you have Class B fires, which are fueled by liquids or liquefiable solids. Think petrol, oil, paints, solvents. Knowing these differences isn't just trivia, it's absolutely crucial, because the specific fuel dictates exactly how you have to fight the flames. Next, Class C represents dangerous gas fires, fuels like natural mains gas, butane, or propane. And then there's Class D. This is a highly specialized, heavy industrial hazard involving combustible metals. If you work in a facility handling magnesium, potassium, or sodium, a Class D fire is a terrifyingly real threat. And you need highly specific extinguishers for it, because if you throw standard water on a Class D metal fire, you could actually trigger a massive, deadly explosion. Finally, we have Class F, which covers fires involving high-temperature cooking media, like deep fryer vegetable or animal oils. Because these burn so incredibly hot, over 360 degrees Celsius, your standard liquid extinguishers just won't cut it. We also have to talk about electrical fires. Now, electricity isn't officially its own standalone class, but it's a unique ignition source that will endlessly feed a flame. But here's the trick. Once you safely cut and isolate that power supply, the fire can usually just be treated like a standard Class A solid fire. All right, Section 3, how fire spreads, the physics of heat transmission. Okay, so direct burning is one thing, but thermal energy actually travels and spreads in three distinct ways. First is conduction, where heat passes directly through a solid object. Imagine intense heat traveling right along unprotected structural steelwork or metal plumbing pipes, and suddenly igniting a completely different room down the hall. Next is convection. This is heated fluids or gases circulating and rising. It's exactly why hot, highly toxic gases rush upward through open stairwells and elevator shafts, quickly spreading fire to upper floors. And lastly, radiation. This beams intense infrared heat straight across empty space, casting a shadow just like a flashlight would. It travels in a straight line and can literally ignite distant objects or even the building next door if it's too close. Which brings us to Section 4, defeating the threat, preventing and containing fire. The core logic of fire prevention is just beautifully simple, but absolutely profound. It all circles back to that fire triangle. If you rigidly and systematically separate the fuel sources, the oxygen sources, and the ignition sources, well, you starve the fire before it can even exist. Basically, fire prevention is literally just the act of keeping the three sides of that triangle as far apart as possible. A really great practical example of this is when you're dealing with highly flammable liquids, or HFLs, like solvents and thinners. These things produce heavy, incredibly flammable vapors. You can anchor your entire safety strategy to the acronym VICES. Check it out. Ensure proper ventilation so those dangerous vapors don't build up. Remove all ignition sources. Guarantee containment in fire-resistant cabinets, meaning you keep no more than 50 liters out in a workroom. Exchange those highly flammable liquids for safer alternatives whenever you possibly can. And lastly, separate them completely from any other stored materials. But of course, we live in the real world, so we have to prepare for the worst. If prevention fails and a fire does break out, we rely heavily on passive fire protection, specifically a brilliant strategy called compartmentation. Think of this as building a specialized, heavily armored box inside the building, using fire-resisting walls, floors, and ceilings. The whole goal is to trap the fire and smoke inside that specific compartment for a set amount of time. It severely limits the spread, keeps property damage down, and most importantly, it buys people enough time to get out alive. But please, remember this absolutely critical non-negotiable rule. A fire compartment is completely useless if its boundaries are compromised. It is literally only as good as its weakest link. If you've got unsealed holes where plumbing pipes punch through walls or unprotected ventilation ducting, or, and this is the absolute worst, a heavy fire door that someone casually propped open with a wedge, the compartment is totally broken. The smoke and fire will just bypass those protective walls like they aren't even there. And that right there is exactly why specialized fire-resisting doors are mandatory and, frankly, highly engineered pieces of tech. They are tested as one complete set: the hinges, the glass, the frame, everything. And they're rated to give you 20, 30, 60, or even 120 minutes of solid protection. For timber fire doors, they require very specific tiny 2 to 4 millimeter gaps around the edges. And tucked inside those gaps are intumescent seals. In the early stages of a fire, the rising heat hits those seals and causes them to literally expand and swell up, tightly sealing off the doorframe and blocking the passage of deadly smoke and flames. So as we wrap up this explainer, I want you to take the science and the structural rules we've talked about today and actually apply them to your own life. Take just 1 minute today to look closely at your environment, your office, your workshop, even your home. Ask yourself a simple question. If the fire triangle somehow completed itself right now, what is the weakest link in your fire compartment? Seriously, finding it and fixing it today might just save a life tomorrow. Thanks so much for joining me, and keep learning.